This is Chapter 4, Reactions in Aqueous Solutions, which is a fairly broad chapter, and it covers a lot of things that you guys did last year, and some things you probably didn't do. So we're just going to kind of get a feel for some of this, and we'll get into more detail in later chapters. So I'm going to really breeze over some of this information, so don't worry too much about that. And any questions you have, of course, you can ask in class. So, solutions. We define a solution as two substances that are uniformly mixed together and as homogeneous or homogeneous, whichever you prefer. The solvent is the thing that's doing the dissolving. You have more of it. And the solute is the thing that's being dissolved. Dissociation is the process of when you have an ionic substance that is being pulled apart by typically water in a solution. It's called dissociation. And what happens is you have the positive end of a water molecule pulling on the negative ions, and then just the opposite, the negative side of a water molecule pulling on the positive ions. And this is why certain things like salt dissolve in water really well. What it forms is because of these positives and negatives, it forms what's called an electrolyte. So you can have electricity flowing through a ionic solution. Now you also can have other things that dissolve in water. For example, ethyl alcohol, methanol. These things will dissolve in water as well, but they don't conduct electricity, so therefore they are called non-electrolytes. If it doesn't form ions in solution, it's a non-electrolyte. So just a couple examples here. Anything that is ionic, so metal versus non-metal combinations, they're all electrolytes. There are no weak ones or non-electrolytes, but if it's molecular, a lot of different things could be going on here. So for example, hydrochloric acid is a molecular substance, even though they are both non-metals. But in any case, it's a molecular substance and it's a strong acid. It's a very good electrolyte because it completely separates or dissociates in water. As far as a weak electrolyte, that would be a weak acid. An example of that would be vinegar or acetic acid, same thing. They don't dissociate very well in water. And then what else do we got? All other compounds. Well, how about sugar? Sugar dissociates, it dissolves in water, but it doesn't form ions. It does separate into sugar molecules, but it doesn't form ions, so it's not an electrolyte. It's a non-electrolyte. This little test here we'll actually do in class to kind of show the difference between these things. If it is an electrolyte, it will conduct electricity really well and light up a light bulb. And it's better to see this in class as far as talking about it here. Just another example or something I don't think we've mentioned up yet. We'll see it again later in this lecture. Strong acids. You want to memorize this list because they'll come up here or there. As far as the easiest way that I know to memorize these is the top three are halogen compounds or molecules. So you have hydrochloric, hydrobromic, and hydroiodic. That's a funny one to say. And then the bottom two here, nitric and sulfuric, they're just really common. You see them a lot, so they're easy to know. The ones that students have the most difficult time with are chloric and perchloric acid. They're just really, really strong acids, and I guess you just have to memorize them. As far as bases, these are all strong acids and strong bases. Group 1, remember all those group 1s are really reactive, so they do a really good job as far as dissociating or separating in solution. So if you see an OH hydroxide paired up with a group 1 metal, it's a strong acid. And then for group 2, the ones that are a little lower on the list, calcium, strontium, barium, they also are strong bases. Not magnesium, it's not one of them. And I don't know where this is going. We'll just pass on this. As far as precipitation reactions, you guys did some of this last year. In double replacement reactions, you have two clear liquids. You did a lot of this in your qual lab. You mix some things together in a solid forms. Usually you can tell by either it being some color or it's white, and that is a precipitate. Metathesis reaction, we typically don't use that very often, but that would be kind of another word for a double replacement reaction. I guess this is a point we can mention here, but I'm not going to worry about it too much right now. The molecular equation tells you specifically what you started with and what you ended with, but when you get to the AP exam, a lot of times they're not going to want all this information because you have a lot of spectator ions that really aren't doing anything in the reaction. So as an example, when I put silver nitrate in solution with potassium chloride, I end up getting a precipitate of silver chloride. It's a white, kind of purplish looking precipitate. And then I have some potassium and nitrate ions floating around at the end. Well, nitrate was there at the beginning and nitrate was there at the end. It didn't do anything. Potassium was there at the beginning and was there at the end. It also did not do anything. The only ones that were involved in the reaction were silver and chloride, and they made up the silver chloride. So that's really the only thing I care about in this reaction. So going through here, I thought I had it listed out there. So in any case, the net ionic equation is simply going to be, maybe I have it listed somewhere else, but I'll go ahead and write it. Silver plus chloride ions giving us, and those were aqueous, but I am going to leave that off. Silver chloride solid. That's the only thing you need to write, the net ionic equation, the things that actually participated in the reaction. We mentioned this already as far as some of the acids, strong acids, but I guess we'll see those again a little bit later. They kind of combine a couple of the more common namings or groupings of acids. The first one is by a guy named Arrhenius, Svante Arrhenius, I believe. And the other one is a combination of two other chemists, Bronsted and Lowry. Let's go with Arrhenius first. The way he looks at something that's an acid is something that donates hydrogen ions in a water solution. He also mentions bases, which we'll see here a little later, are things that donate hydroxide ions to a water solution. Bronsted, Lowry, they're a little bit different. As far as with the acids, again, they mentioned, Arrhenius mentioned that it donates hydrogen ions to a water solution. Bronsted, Lowry say it's donating protons. That's it. Something that donates protons. You could also call it a hydrogen ion. But it's anything that donates a proton. And again, here's our strong acids. You need to memorize those. Bases, Arrhenius, as we've mentioned earlier, donates hydroxide ions in water. Bronsted and Lowry don't go that route. They say it's something that accepts a proton or a hydrogen. That's it. So Bronsted, Lowry is really the definition that we typically use in chemistry. The way I like to think of it is follow the protons or follow the hydrogen. Acids donate hydrogens and bases accept hydrogens. That's it. Alright, this is probably a good place to stop, and we'll start up the second lecture in just a moment.